The Milky Way is dying. Not dramatically, not in a single cataclysmic event, not in any way you would notice if you stepped outside tonight and looked up at the same stars that have always been there. The death of a galaxy is not an explosion. It is a slow withdrawal, a gradual dimming, the quiet exhaustion of something that has been burning for 10 billion years and is beginning finally to run out of the things it needs to keep going. And the most remarkable part of this story is not how the Milky Way dies. It is that by every meaningful measure, the dying has already started. To understand what is happening to our galaxy, we need to go back to a moment in cosmic history called cosmic noon. Approximately 10 billion years ago, roughly 3 billion years after the Big Bang, the universe was doing something it has never done before or since. It was forming stars at a rate so extraordinary that nothing before or after comes close. Across every galaxy in the observable universe, gas was collapsing into new stars at a pace that represented the absolute peak of the universe's creative output. Not 10% more than today, not twice as many. At cosmic noon, the universe was forming stars at a rate approximately 30 times higher than it is right now. Cosmic noon was the universe at full brightness. Everything since has been a slow sunset. To understand why cosmic noon happened and why it cannot happen again requires understanding the relationship between galaxies and the cosmic web they are embedded in. In the early universe, the cosmic web was more active, more turbulent, more effective at funneling fresh gas into galaxies along the dark matter filaments that connect them. Galaxies at cosmic noon were not simply using what they had. They were actively receiving new material from their surroundings, cold gas streaming in along filaments and providing continuous fuel for star formation at rates that would be impossible to sustain from internal reserves alone. As the universe expanded and aged, two things changed simultaneously. The filaments of the cosmic web became more diffuse, the gas within them more spread out, the inflow rates into individual galaxies declining, and dark energy began to assert itself more strongly, accelerating the expansion of space and gradually stretching the distances between galaxies and the cosmic structures that feed them. The pipeline that delivered fresh gas to galaxies at cosmic noon did not shut off overnight. It narrowed gradually over billions of years, but the direction of change has been one way only. The Milky Way is receiving far less fresh material today than it was at its peak, and the rate of that inflow will continue to decline as the universe continues to expand. The Milky Way itself was different at cosmic noon. It was smaller, more chaotic, more actively engaged in the business of assembling itself. Gas was pouring in from the surrounding cosmic web. Dwarf galaxies were being cannibalized and their stars incorporated into the growing structure. The rate of star formation in our galaxy at that period was many times higher than it is today. New stars were igniting continuously across the disk, each one a fusion engine that would burn for millions or billions of years, adding its light to the collective output of the galaxy. But the gas was not infinite. That is the fundamental constraint that governs everything about a galaxy's lifespan. Stars are made of gas. When gas collapses under gravity, ignites fusion, burns through its hydrogen, and dies, it returns some material to the interstellar medium. But not all of it. A fraction of the gas that goes into making a star is locked up permanently in the stellar remnant that the dying star leaves behind. A white dwarf or a neutron star or a black hole. Over billions of years, star after star after star converts gas into locked-up remnants that can never form new stars again. The total supply of available star-forming material in the galaxy decreases with every stellar generation. The Milky Way is currently forming new stars at a rate of approximately 1 to 3 solar masses per year. That sounds modest, and it is. Compare it to the starburst galaxies we observe in the distant universe, some of which form hundreds of solar masses of new stars every year, and our galaxy looks like it has already wound down to a maintenance level. The gas reservoir that drives star formation is being depleted. The fresh gas inflow from the cosmic web that sustained the high formation rates of cosmic noon has slowed dramatically as the universe aged and the cosmic web became less active. Our galaxy is running on what it has rather than what it is receiving. The depletion of the star-forming gas reservoir is not simply a matter of stars consuming gas and leaving remnants behind. There are additional mechanisms actively removing gas from the galaxy that accelerate the process beyond what stellar consumption alone would produce. When massive stars reach the end of their short lives and explode as supernovae, they release enormous quantities of energy into the surrounding interstellar medium. That energy heats the nearby gas, sometimes to temperatures high enough that it escapes the gravitational pull of the galaxy entirely, streaming outward into the intergalactic medium where it can no longer participate in star formation. The very process of star formation contains within it the seeds of its own suppression. Sagittarius, A star, the supermassive black hole at the center of our galaxy, adds another ejection mechanism. In its current state, Sagittarius A star is relatively quiescent, occasionally consuming small amounts of material, but not actively driving large-scale gas outflows. But the history of the galaxy contains periods of much greater central activity, and future merger events may reactivate it. When supermassive black holes enter active phases, they can drive powerful jets and winds that sweep gas outward from the galactic center across kiloparsec scales, removing enormous quantities of potential star-forming material from the galaxy in geologically brief periods. The black hole at the heart of our galaxy is not currently killing it, but it has contributed to the gas removal process in the past and will likely do so again. The universe as a whole has already passed through this transition. The overall star formation rate of the observable universe today is approximately 3% of what it was at cosmic noon. The universe is not dead. Stars are still forming. But the golden age of stellar creation is 10 billion years in the past. We are living in the long declining afternoon of a universe that had its morning and its noon and is now moving, slowly but irreversibly, toward its evening. One astronomer described it this way: "Cosmic noon was a long time ago. By now, the universe has reached cosmic evening. It is not nighttime yet, but things have definitely slowed down. The Milky Way's current star formation rate, already low by cosmic standards, is not going to increase. The processes that could interrupt the decline, a fresh injection of gas from a major merger, a period of intense starburst activity triggered by a gravitational interaction, might temporarily increase the rate but cannot reverse the long-term trend. The reservoir is finite. The formation rate will continue to decline. The last stars will eventually form from the last available gas, and after that, the galaxy will begin the very long process of going dark." How long is very long? The current generation of massive stars, the ones burning most brightly in our galaxy right now, will exhaust their fuel and explode as supernovae within millions of years. That sounds fast, but it is already happening, and it is part of the normal cycle. The medium-mass stars like our Sun will last for billions of years. The small, dim red dwarf stars, which make up the majority of stars in the galaxy, will burn for trillions of years. When the last red dwarf finally exhausts its fuel and fades, the Milky Way will be a collection of cold, dark stellar remnants, white dwarfs slowly cooling toward absolute zero, neutron stars spinning down, black holes the only things remaining that still have any significant gravitational presence. Astronomers have already mapped what this graveyard looks like within our own galaxy. A 2022 study from the University of Sydney modeled the distribution of stellar remnants across the Milky Way and found that the galaxy already contains approximately 1 billion neutron stars formed from the deaths of massive stars over the galaxy's history. Most of these objects were born with explosive kicks that sent them moving through the galaxy at high velocities. Unlike living stars which orbit the galactic center in relatively stable paths, these remnants travel on complex orbits, threading through interstellar space, never slowing down, never settling. Ghost-like relics of stellar deaths that occurred billions of years ago. The galaxy we inhabit is already partly a graveyard. The living stars we see are embedded in a population of invisible dead ones that outnumber them in ways we are only beginning to quantify. The long-term fate of those remnants extends across timescales that make the current age of the universe seem brief. White dwarfs, the most common type of stellar remnant, cool over trillions of years, radiating away their residual heat until they become cold, dark objects called black dwarfs. The universe is not yet old enough for a single black dwarf to exist. The cooling time required is longer than the current age of the cosmos. But given sufficient time, every white dwarf in the Milky Way will eventually make that transition. The galaxy's future state, after the last red dwarf burns out in perhaps 10 trillion years, is a collection of black dwarfs and neutron stars and black holes, moving silently through space that contains no new light, no new fusion, no new warmth. Not destroyed, just finished. This is not a prediction, it is physics. Every star in the galaxy is burning through a finite supply of hydrogen. Every one of them will run out. The question is not whether the Milky Way goes dark, but only when, and what happens before it does. Here is where Andromeda enters the story, and here is where it gets more complicated than anyone expected. For most of the last century, since astronomers realized that Andromeda was approaching us rather than receding, the collision of the Milky Way and Andromeda has been treated as essentially inevitable. By 2012, detailed measurements of Andromeda's motion using the Hubble Space Telescope had produced what looked like a definitive result. Andromeda was on a direct collision course. In approximately 4.5 billion years, it would strike the Milky Way, triggering a dramatic galactic merger that would destroy both spiral structures and produce a single giant elliptical galaxy, sometimes called Milkomeda. That picture was accepted so widely and for so long that it appeared in textbooks, in NASA visualizations, and in dozens of YouTube documentaries, including the competitor video that inspired this one. In June 2025, a team led by astronomer Till Sawala at the University of Helsinki published a paper in Nature Astronomy that ran 100,000 simulations of how the local group will evolve over the next 10 billion years. Their paper incorporated the most precise data available from both the Hubble and Gaia space telescopes, and crucially it included something previous studies had underestimated: the gravitational effects of the Large Magellanic Cloud and the Triangulum Galaxy on the Milky Way and Andromeda's trajectories respectively. What those simulations found overturned a century of accepted wisdom. The probability of the Milky Way and Andromeda colliding in the next 4 to 5 billion years dropped from near certainty to approximately 2%. The probability of any collision within the next 10 billion years dropped to roughly 50-50. In half the simulations, the two galaxies pass each other at a distance of roughly 5 times the Milky Way's diameter and continue to evolve largely independently. In the other half, they eventually merge, but later and less directly than previously predicted. The Large Magellanic Cloud is the key factor. It orbits the Milky Way at an angle perpendicular to the Milky Way Andromeda orbital plane, and its gravitational influence pulls the Milky Way sideways, off the trajectory that would lead to a direct collision with Andromeda. This is not a small nudge. The Large Magellanic Cloud, despite being only about 15% of the Milky Way's mass, gravitational influence to fundamentally alter the probability of the most anticipated cosmic event in the history of our galaxy. Sawala himself said it clearly. The fact that there is only around a 50-50 chance of a merger was very surprising. But here is the deeper implication that most coverage of this paper missed entirely. Whether Andromeda hits us or not, the Milky Way is still dying. The collision story was always about the timing and the drama of the galaxy's transformation, not about the fundamental process of stellar exhaustion that is already underway. If Andromeda does hit us in 7 or 8 billion years, as the new simulations suggest is most likely in the merger scenarios, the collision will trigger a brief but intense starburst as the gas reservoirs of both galaxies are compressed and ignite all at once. New stars will form at an accelerated rate. The night sky of whatever world exists at that moment will blaze with new stellar nurseries. But that starburst will burn through the remaining gas even faster. The merger does not save the Milky Way. It accelerates the exhaustion of its remaining resources. The collision scenario produces a more spectacular final act, but an earlier last star. And if Andromeda misses us, the Milky Way continues its slower decline, forming stars at a decreasing rate from a depleting gas reservoir until the last generation of stars forms from the last available material, and the galaxy begins its trillion-year cooling into darkness. The Large Magellanic Cloud itself adds another layer. The simulations that showed Andromeda might miss us also confirmed that the Large Magellanic Cloud is almost certain to merge with the Milky Way within the next 2 billion years. That merger will be a significant event for our galaxy, disrupting its structure, possibly disturbing the central supermassive black hole Sagittarius A star into a period of intense activity and triggering its own starburst. It is a preview of the galactic reshaping that is coming regardless of what Andromeda eventually does. Further data from the Gaia Space Telescope, expected in the summer of 2026, will refine the measurements of Andromeda's transverse motion and reduce some of the uncertainty in the collision probability. We may soon know, more precisely than we currently do, which half of the simulations we are actually living in. Whether Andromeda is on its way to merge with us, or whether it will pass and recede and leave us to our slower, independent decline. Either way, the answer to the fundamental question does not change. The Milky Way peaked at cosmic noon 10 billion years ago. It has been declining since. The star formation rate has dropped from its maximum to approximately 3% of that maximum and is continuing to fall. The gas reservoir that powers new star formation is being depleted with every stellar generation. The universe itself has passed through its productive peak and is on the long, slow path toward the darkness that thermodynamics ultimately demands of any finite system. Andromeda, approaching at 110 kilometers per second from 2.5 million light-years away, is a dramatic detail in that story. It changes the timing of certain events. It adds spectacle to a process that would otherwise be quiet and gradual, but it does not change the destination. The stars are running out. The galaxy is dimming. The death is not coming. It has already started. Whether Andromeda joins us for the ending is, cosmically speaking, a minor detail. Good night.